Okay. 5% solution sodium acetate. Acetate is C2H3O2, correct? Yes. A 5% solution of sodium acetate by mass. I want to calculate the following, okay? I want to calculate, let's see, where shall we put it? I'll pan over this way a little bit, okay? I'll pan over this way a little bit, and I can use the rest of the board over here. And I want to know the pH, the POH. I want to know the H-ion concentration or the hydronium concentration, same thing, correct? I want to know the OH concentration. I want to know all the equations. And I want to know the equilibrium expression. Equilibrium expression. Expression. Okay? I want to know the equilibrium expression. Okay, here we go. You ready? Okay, what do we got so far? I did some work. All right, we know that this is acetic acid, that there's this flow of electrons to the C double bond O. It makes this slightly polar. Therefore, the hydrogen can be removed. We know, however, that acetic acid is a weak acid. That's the Ka for that, so it's a weak acid. That's very important when we try to figure out what's going to happen when we're putting 5% sodium acetate solution, sodium acetate into water, and we're making that solution. We want to know what's happening chemically. Okay, so you have everything down, right? You want to calculate the molarity of that solution. Well, if it's 5 grams per 100 milliliters of solution, then it's going to be 50 grams in 1 liter. Convert 50 grams of sodium acetate to moles divided by 82. That's the atomic weight of sodium acetate, or the formula weight. I don't like to use all those terms. I just say the atomic weight. Okay. So it's going to be 0.61 moles. It's going to be in 1,000 milliliters. So that's the molarity, correct? So what have we done? We established that sodium acetate, that acetic acid, HAC, is a weak acid. That's critical. We've established that. Are you okay with that, Enzo? Okay, good. We established the molarity of the sodium acetate solution. We also know, based on our discussion, that in the sodium acetate solution, if I have one sodium acetate particle right here and it completely dissociates, so I have one particle of sodium acetate, correct? If it dissociates, I have one particle of sodium and one particle of acetate. So, what's going to be the molarity of the acetate ion? The molarity of the acetate ion will be 0.61, correct? If I had 6 of these, right? If I had 6 of these, and I ripped these in half, I'd have 6 and 6, correct? Yes? 6 sodium, 6 acetate. Okay, good. So now we know that acetic acid's a weak acid. We know why. We know the molarity of the solution. What else do we know? We know the molarity of the concentration, the molar concentration of the acetate. And that's, we know the Ka, Kb. To get the K, if I gave you the Ka, if I gave you this, to get the Kb, you divide Kw by Ka, that gives you Kb, right? So in other words, 1 times 10 to the negative 14th, that's Kw. Okay? Memorize that. That's a good thing to memorize. If you're walking down the street and you say, I'm in the mood to memorize something, that's a good one. Okay? Equals 1 times 10 to the negative 14. Okay? So 1 times 10 to the negative 14 divided by 1.8 times 10 to the negative 5th. I still remember that from college. We did so many problems with HAC, it's overwhelming. All right, good? So I can erase a lot of this stuff? Yes? Okay? I'm going to erase all of this. I'm going to erase everything. Okay? Because we memorized, you memorized all of that, didn't you? 5.56 times 10 to the negative 10th, right? Yep. 1.8 times 10 to the negative 5th. You did all that, right? Yes? You wrote it down, you memorized it. You already memorized it because you're from Missouri, and Missouri people have to see it to believe it, and then they memorize it. Excellent. Okay, now, so what do we got? I have sodium acetate. I have the acetate. What's it doing in solution? It's doing this. It's going, the acetate ion is combining with the water, and I'm producing HAC plus what? Plus OH, -1. Why is that happening? That's happening because that is the anion of a weak acid. So that weak acid wants to stay together, doesn't it? So what's it going to do? In order to stay together, it's going to do what? It's going to say, wait a second, I'm going to be put into a pool of water. I'm going to take the hydrogen. Oxygen is not going to want to give up 2 hydrogen. I know what you're saying. Somebody said it before. It takes all the hydrogen, you're going to get oxygen bubbling up. No. This only happens with electricity. You take salt, you put it in the water, you run electric current, and you separate it into hydrogen and oxygen. It's the only way you can do it. You're not going to do it by putting an anion of a weak acid in. It's not going to happen. The oxygen is only going to give up 1 hydrogen, not 2. It's not going to happen. Okay? So now, what do we have? We have this. So, the acetate ion is what? An acid or a base? It's a base because it produces OH. So that's a base. So a solution of the acetate ion will be basic, correct? Therefore, that's the equation. That's the equation. Now, we don't use water in our expression. Let me explain. I didn't really teach you much about equilibrium because we had to get to acid-base chemistry. So let me explain to you what the KEQ, in other words, the equilibrium constant is and how you get it. Okay? Let's say I have a reaction, a chemical reaction, and it's going to be A plus B. You have equilibrium where it goes back and forth depending on conditions, right? And you get C plus D. The equilibrium expression is going to be, let's say that this is water. Let's just call it W, okay? We're just going to call it W, okay? It doesn't have to be. You can write a KEQ, and you can write a KEQ, and it doesn't have water, but I just want to make a point, okay? So the equilibrium expression is going to be KEQ sub EQ equals the product of the products, the molarity of the products, the molarity of C times the molarity of D, the molarity of A times the molarity of W. It's water in this case, correct? Are you with me? Are you with me? Now, what would happen if this was a 2 here? It was balanced and it was a 2. Wouldn't you have 2 molarities? The same thing? Wouldn't it be 2 times the molarities? Wouldn't it be? Right? In other words, you could literally say, and I wouldn't be breaking any rules, but it would be weird. Couldn't I say D plus D? Couldn't I?
Yeah.
Mathematically? Sure. So I have 2 of that product. So what would you do if that were true? You would go like this. You'd square it. Because it would be D times D, which is D squared. So these coefficients go down here. But I didn't teach that. But it makes sense though, doesn't it? Okay? So, now, what happens is we don't use water in this equation. We say that it happens in the presence of water. But we don't use the water in the expression. Let's multiply both sides by water. What happens? Doesn't the water cancel? Right? Yes? Doesn't it?
Yes.
And what are you left with? You're left with what? If this is a base expression, that would be KB. Right, Kate, right? Yes, do you get it? So I'm multiplying. Now, let me look at your textbook. Let me show you where in the textbook this is. Look at your textbook and look at page... Look at page 665. Let's say that this was an acid expression. Okay? For instance, I want to erase this. Okay? I want to erase that for a minute, okay? Is that all right? So look at the bottom. Okay? It would be KEQ. It would be times what? Times water. Right? And then that's going to, we'll say this is basic. We'll say take out the water and we're left with what? What are we left with? We're left with KB time is going to be HAC times OH divided by AC negative. You see that?
Yeah.
You get that? So what they say is, if you multiply the KQ by water, you get KB. If it's a KB expression. You would get KA if it were a KA expression. Clear? But this is clearly a KB expression. Are you with me so far?
Yeah.
Yes? Okay, good. So therefore, that this equals a KB expression. All right, now let's plug in. Okay? We're going to plug in. We're going to say 5.56 times 10 to the negative 10th equals, when this dissociates, am I going to get equal quantities of this and this?
Yes.
Yes, because for every H that AC takes, I'm going to get a OH, right? So, doesn't HAC equal OH? Doesn't it? Aren't they equal? So let's call OH X. HAC would be X, correct? So wouldn't it be X squared? Yes or no?
Yes.
Yes. Now, let me ask you one more thing. This is going to be 0.61 molar. Aren't you losing? Shouldn't I be subtracting off of the AC because some of this is going to be being converted? So shouldn't this be, this is X, shouldn't this be minus X? Shouldn't I say that quantity, 0.61 minus X? Shouldn't I? Right? Because that value is not 0.61, is it? That value is that minus the X, isn't it? Well, what happens is this. that creates a quadratic equation, and you can do that. But this is the rule, and I'll show you when I do buffer systems later on. And that is this. Isn't that a very small number? Isn't that a very, very, very small number? So isn't x in reality going to be very tiny? Isn't it? So the amount that you're going to subtract off 0.61, isn't it going to be so tiny that it really doesn't matter? It doesn't matter. It's so tiny. A lot of teachers call it the 5% rule. In other words, unless x is at least 5%, and that has nothing to do with the original equation, the original solution I'm doing, it's something different. But it's got to be a relatively large number to affect that. Because if it's so small, 1 minus a billionth, is it still about 1? 1 minus a billionth, right? What does that mean? What's a billionth? Tenth? That's hundredth, right? Thousandth, right? 10,000ths, 100,000ths, millionths, 10 millionths, 100 millionths, billionth. Isn't that billionth? Tenth, hundredths, thousandths. What's that? Sorry, am I wrong? Sorry. This is tenths, hundredths, thousands, 10,000ths, 100,000ths, millionths, 10 millions, 100 millions, billions. Right? What's 1 minus that? Isn't it still approximately 1? Wouldn't the precision be far too great to care? Isn't it going to be 1? Yes or no?
Yes.
So you don't really need, because this is, if you put it in scientific notation, it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It's even larger than that, isn't it? 10 to the 10th, right? Is 10 billionths, right? Right? 10 to the negative 6 is millionth, 10 to the negative 9th is billionth, 10 to the negative 10th is 10 billion, so it doesn't matter, okay? Now, so what I'm going to do is, I'm going to solve for x. That's where I am. Okay, I'm going to stop there, and I'm going to call it quits. But, if you come up during your after lunch, you have, what do you call it, recess? What do you call it? Just hanging out?
We have recess first.
You have it first. Okay, well, I've got to go get something to eat because I'm really hungry. But if you're here when I come back and I can eat and take care of business, then, and I can film this and finish it, I'll give you extra credit. Clear? Are we there? Have a good day.